inside, the meanwhile is effective there. Okay, he has been coordinating this third work package, which is on plastic interaction and the survey on work that was involved in plastic simulation and quantum survey.
Okay, so thanks very much. So as you see, I'll be speaking on classical simulation of quantum circuits, and my talk will not really be a tutorial as such, but more a kind of a survey with some extra explanatory remarks. And I want to kind of gear the content to cover the highlights, or some of the highlights of these three recent papers I've listed here, which are kind of related to the QICS project, so that's kind of appropriate. And these works were done in collaborations with various people, Akinaz Miyake, who we met this morning, Barbara Kraus, John Montrose, Nick Bremner, and Dan Shepard. And I think many of these are associated with the QICS network. Okay, so I want to begin with some just a few remarks about the significance and context of studying simulations. Often in our subjects we hear these rather fundamental sounding questions, but which are also rather vague. In fact, we heard some this morning in Akinaz's talk. So for example, how can we compare classical and quantum computing power? What are the essential quantum features that provide information processing capabilities beyond classical computation in this subject? So these are all very vague questions, and the point is that the study of classical simulation of quantum circuits or quantum computations provides a kind of mathematically precise, concrete approach to these questions. And so, for example, if you were to, well, after all, it addresses precisely the classical computational resources that are required to reproduce the outputs of quantum computations. So that's really the first question directly addressed. And if we restrict ourselves to just particular classes of computations, not the most general ones, we can sort of study, we can think of a restricted class as embodying some specific kind of feature that we might be interested in. And we can explore the relationship between classical and quantum computing both from above and below, as I say here. We can sort of try and provide evidence that some classes of computations are actually hard to simulate classically. That is, that quantum computing should be more powerful than classical, although I guess we all know there's no actual proof of this, and the problem really is that classical hardness results in notoriously difficult, like the P versus NP question, things like that. But we can provide similar kinds of evidence. Instead of proving outright hardness, we would prove, for example, that efficient simulation of some computation would imply something catastrophically implausible, like the complete collapse of some complexity class, such as NP equaling P, or something similar to that. And from below, we can study the relationship by looking at classes of quantum computations, of restricted ones, which you can simulate classically. So you might think this shouldn't be very interesting, because these are computationally lame. These are the things that don't provide you with any computational benefit of classical computing, so why should you be interested in this? Well, they turn out to be extremely interesting because there are various very non-trivial interesting such classes known, and they involve lots of rich quantum effects, and it sheds a lot of light on this second question here. And it turns out it's not just a matter of saying that quantum computing is more powerful than classical, but there's a very rich structural relationship between the two, and you can embed, so sort of schematically, you can embed classical computation into quantum in many different inequivalent ways, and we're still exploring new ways, and if you're irreverent enough, you might even consider, is there anything left over once we put all these things down? And it's quite possible that they might not be, so, although you probably wouldn't be here today if that were really, people believe that were the case. Okay, so let me now move on to say a little bit more precisely what we mean by an efficient simulation of a quantum circuit. So this is kind of the simplest version of this, and there'll be a slightly more elaborate one later. So what description of a circuit. So this, for example, you can think of as just a list of gates and the lines on which they act, and we're given its input, which is just a bit string. So that we can always just think of this as a computational basis state, and the output is just a designation of which lines we're going to measure to get the output, which is sometimes one line for decision problems where you have a one-bit output, but sometimes, crucially, it will need to be more. And this whole description is just kind of a classical thing. It's a great big bit string, if you like. It's a description of, say, a quantum computation, and it has a certain size, the length of this description, which you can think of, for all intents and purposes, as actually being the size of the circuit, the number of elementary gates. So it has some size n, and this parameter n is very important for us because in complexity theory we're always concerned with how computational resources grow as a function of increasing instances of the problem you're solving, bigger and bigger input instances. So we think of this as being the size of the circuit here. Okay, so given that description, we can ask for various things, and I just want to distinguish two. There's so-called weak simulation or a strong simulation, classical simulation. So simulations will always be classical. So a weak simulation simply means we want a sample of its output distribution by classical means. So given this description, I want to sample what it would do, but using a classical computer in polynomial time, with randomized classical choices as well. And sometimes we don't even ask for an exact sampling of the exact distribution, but a suitable approximation will suffice. Okay, so that comes up in various different contexts. So that's a weak simulation, it's just a sample of a probability distribution, and a strong simulation is asking for rather more. We want to calculate any one of the output probabilities. We want to know what the actual probability is in polynomial time, again, classical polynomial time, and if there's a precision issue, then we want a polynomial in the number of digits as well. Okay, often there isn't a precision issue because circuits are described in terms of gates with simple entries like 1 over root 2s and integers and so on. But sometimes you might get a more complicated situation. So for example, this might be a description of a quantum circuit of size order n, made up of Toffoli and Hadamard gates, standard input, a single output measurement, and then a weak simulation is directly what the quantum process itself will give you. So note that even the quantum process itself does not tell you what the output probability is. It just enables you to sample, when you run it once, to sample the output probability distribution. Okay, so it's instructive here just quickly to sort of say a few words about the relationship between weak and strong simulations. As the name suggests, strong does imply weak, but it's not immediately obvious how this works. So suppose, there are n lines in the output. You could have exponentially many output probabilities, like 2 to the n of them. And even if you can calculate each individual probability in polynomial time, how does that enable you to sample the distribution, which is what we want for the weak distribution? So there's kind of an adaptive trick to do that. But in order to do it, we need not just the probabilities, but we need the marginal distributions as well. So, of course, if you know the probabilities, you can compute the marginals by summing out some of the variables. But the trouble is, if you want the marginal on a single variable out of n, that's an exponentially big calculation, so that's no good. So we simply demand up front that in the strong simulation that we're given the marginals as well in polynomial time, that there's some way of computing that. And then we're just, if you want to sample, say, 3 things, you calculate the probability of x1, that's one of the marginals, then you sample it, get some value, say 0, and then you successively sample the others given what you've already seen. Then you compute the probability of x2 given x1 was what you got, which is, by Bayes' rule, this quotient of 2 marginals. So you compute that and then sample that and get another bit, and then you compute the probability of x3 given the 2 that you already saw as a quotient of marginals and so on. And you carry 2n of the probabilities, or the marginals, rather than exponentially many of them. Okay, so that shows strong implies weak, but we don't expect weak to imply strong, because that would indeed have catastrophic effects. Well, depending on how it's catastrophe. So, and you can see that very easily. Suppose you have a Boolean function from n bits to 1 bit, so f of I up to in, and let a be the number of satisfying assignments, the number of bit strings which give value 1. Then if you have a quantum circuit that computes this function, then you consider this process. You take all zeros, apply Hadamard's, you get equal superposition of all the bit strings here, you evaluate the function, you measure its output qubit, and then the probability of seeing 1 is then easily seen to just be the number of 1s divided by 2 to the n. So if you could strongly simulate this very simple process, then that would amount to calculating this probability so you could tell whether it was non-zero or not. And you could get that in polynomial time, and that would amount to solving satisfiability in polynomial time, which is NP complete, so you get P equals NP. And even worse, or better, if you can compute this to good accuracy, you can even learn what A is from its probability and get P equaling sharp P, which is a much bigger class than NP. So however, so strong simulation would imply these things, but weak simulation is easy. You, to sample this distribution, you just uniformly, randomly choose a bit string, I up to in, and compute the function. And that gives you a sample of this distribution because, we've just evaluated it on an equal superposition here. Okay, so therefore we don't expect weak to imply strong simulation unless you think that P equals sharp P. Okay, so right, so I want to say a few words about what you might call direct strong simulation. So, the first thought you might have when you first think about simulating quantum circuits is the idea that, after all, the quantum circuit is just a computable linear algebra process. The input is a vector in the state space, and then you apply gates, which is nothing more than just some elaborate matrices, and you just do a whole lot of matrix multiplications, and then you can compute the probabilities, and compute the components of the evolving state, and so on. But the trouble is that although that's a perfectly good, strong simulation, you can compute anything you like, it incurs an exponential overhead in computing costs compared to the process itself. So, because typically as you apply each extra 2-qubit gate, you can bring another qubit into the state you're considering, and the vector space in which you have to be working to do your matrix multiplications doubles at every step, potentially. The dimension doubles, so you're working with exponentially large matrices when you have just, say, order n size circuits. And more explicitly, perhaps, if you have an n-cubed, a general n-qubit state at the middle of the computation somewhere would look like this with these components. And if you apply, say, a single 2-qubit gate on the first 2 qubits, V, then as a matrix calculation, it's just this product here where you contract over the same labeled indices. But the trouble is, although it's only a 4x4 calculation, you have to repeat it exponentially many times for all the different possible values of the rest of the bit string here. So this shows kind of how the computation becomes sort of exponentially slow compared to what the quantum process itself is doing. It does this in one step. But you also note that if these states are product states, if they're not entangled, if they factorize, it's just products like this, then this update can be efficiently done because you can just separate off all these guys and the V just updates the beginning bit. So this kind of indicates that entanglement is necessary if you want an interesting quantum computational process that can't be mimicked classically easily. So that kind of, in intuitively argues that, in fact, increasing multi-party entanglement is necessary, and people sometimes still say that the power of quantum computation comes from entanglement, which this argument kind of indicates, but that's a wrong thing to say, because all this argument shows that it's necessary, but it's not sufficient. And there are lots of very interesting, very complicated processes that generate lots of entanglement that still can be simulated. And you can even get more mileage out of this simple idea of contracting, sort of multiplying these gates together. And so here's a sort of typical example. So A, B, C, D are the inputs, and these are the gates, U, V, W, and X. And I've labeled, the lines I1, J1, K1, L1, and so on here. And so the final state here has got these four indices, and you take A and B with I, J, and then you multiply it by the gate U, and the output indices I2 and J2, and that feeds into the V and the W and so on. So you write down this expression here with all the indices contracted except I3, J4, K3, and L4, which are these output ones, gives you the actual components of the state at this point. And then, using the usual quantum rules, the probability of doing a measurement, say on the first line, the probability of getting 0, when you put a projector onto the 0 direction subspace there, you reflect the thing across with its adjoint conjugate transpose, and this picture here is a kind of a description of a contraction of tensors like this, where everything's contracted out into a single number, which is the probability. So to compute the probability, you want to compute this, and the point is that you don't have to contract these indices successively through the picture like this, from left to right. You can do more interesting orders of contractions, and then there's this mathematical theory of tensor network contractions. We want to choose the ordering of the contractions so that along the way, the intermediate tensors don't accumulate too many indices. So the trouble is, you see, that if you have k indices, it means you've got 2 to the k components. So if you're able to keep k only logarithmically large, everything will stay polynomially large, your matrices, and you'll be able to do the whole calculation in polynomial time. And so given such an expression, the problem of determining what the optimal contraction ordering is known to be a very hard problem. It's NP hard usually, but you can still get some interesting mileage out of this idea, as was done by Markov and Shi some time ago. And it's interesting to note that this technique of tensor contractions applies to any kind of tensors at all here. There's nothing about quantumness or unitary matrices or anything. It's a kind of much more general thing. So it indicates we're not really exploiting everything we've got in the problem with this technique anyhow. But we still get interesting results, and I just want to quote one just without proof, just to indicate the kinds of interesting things you can get. So you can show that if you have any quantum circuit that has log depth and bounded range gates, you can always classically simulate those. They have no computational power. Log depth simply means that although the circuit can be polynomially sized, you can order the gates into layers, into logarithmically many layers, and within each layer, all the gates can be done simultaneously because they act on disjoint qubits. They can be done in parallel. So so these are kind of very shallow circuits, if you like. In that sense, they're kind of exponentially shallow. And bounded range gates means that the 2-qubit gates act on only a constant number of qubit lines apart at most. For example, they might be nearest neighbor lines, or at most 5 lines apart, or something like that. And so it's sort of amusing then, in light of this, to note that some time ago, Cleveland Montrose showed that the quantum Fourier transform can be approximated very well by a log depth quantum circuit, in fact. This is not the usual textbook circuit you find in all usual books, but it's a more interesting circuit, and it actually has log depth, which the standard one does not have. And you can use that to get a fully log depth circuit complexity classes, and we want to make contact with these two. And the trouble is, a given circuit only accepts inputs of a given size. So in order to deal with these complexity classes, we need to introduce a notion of circuit families, which introduces a slightly awkward extra condition. So general computational tasks we can think of as having a general input, which is any bit string, and the length of the bit string is called the input size, which is just n, the number of bits in the string, and the output is some other bit string, and we're often interested in when the output is only a single bit. So these are so-called decision problems, and associated to such a decision problem, such a computational task, you can associate a so-called language, which is a subset of all strings W which give output 1, or maybe with suitably high probability. This is generally a probabilistic relation between input and output. So for example, you might think of the word as being a number written in binary, and the problem is to figure out whether it's prime or not. So the output would be 0 or 1 according to whether the string is a binary number or not, and the associated language is just the set of prime numbers. So we get these complexity classes of languages because we're interested in those tasks, those languages that can be decided by some specified restricted kind of computational process, like polynomial time or non-deterministic polynomial time or quantum polynomial time or whatever. So we get these languages, and if we want to make contact with circuits now, we have to deal with this issue of having to consider all different lengths of inputs. So we introduce this notion of so-called uniform circuit family, and I'm going to use a definition that's slightly different from textbook definitions. So for us, a uniform family of circuits of some restricted type, perhaps, is going to be a mapping from these bit strings, words of all lengths n, to CW, where C sub W is a description of the circuit. It's a description of the computation you're going to do for the input W. So, and we might as well fix the input to this circuit to be all zeros. I guess you might be more familiar with circuits accepting the input W directly as a bit string, but since I'm allowing my circuits to actually vary with W itself, you might as well standardize the input to be all zeros, and you can just begin with a few NOT gates to turn the zeros into W, since you've got that information there, and then do what you want to do before. So we have this association between all inputs and the computations we're going to do for them. But you have to say a bit more about what this arrow, how this arrow is constructed, because if you don't say anything, then this is a ridiculously powerful construction. For example, you could just hardwire the solution of very difficult computational or even uncomputable tasks into the structure of the circuit. For example, if you think of W as a number in binary, you could simply say that CW is a circuit which outputs 0 or 1 according to whether the Wth Turing machine halts or not. You can solve the halting problem just by fiat, just by defining it to be so. So you want to avoid that kind of embarrassing situation. So you normally require a so-called uniformity condition. You require that this computation of turning the input into a description of its computation should be done in classical polynomial time or some other suitable computational restriction. Now, if you use classical polynomial time, that's suitable for circuits. So, for example, if you have general quantum circuits here, you expect them to be more powerful than classical polynomial time. And here we're kind of prefixing the computational power of the circuit by classical polynomial time. So that's okay if you expect your circuits to be more powerful. But if you're interested in a class of circuits which you expect to be weaker than classical polynomial time, as we will be later on, circuits, then it doesn't make much sense to throw in classical polynomial time with it. You kind of wash out the subtleties of the power of the circuits that you're interested in. So you need a suitably weaker notion of computation, classical computation. And the most natural such thing is classical log space computation, which I'll say more about later on, so I don't want to explain what it is now, only to say that it's a natural notion in classical computation that is believed to be strictly weaker than classical polynomial time. So it's a nice thing to consider when you're in a situation of studying computations, which you expect to be weaker than classical polynomial time too. Okay, so, and just a couple more final definitions here. So we see the power of the circuit computations get supplemented by this uniformity conditions, classical poly time and log space. And the usual textbook definition, which you're probably all familiar with, for uniform circuits is not to have C sub W, but you have C sub N. You have circuits which are parameterized by the input size, not the whole input itself. So, and then all inputs of a given size N get fed into this circuit for doing the computation. But, I mean, that's okay, but the problem there is that the uniformity condition, it's less clear how it combines with the computational power of the circuits themselves, because you're kind of throwing in a computational power, a classical power, that depends only on the size of the input rather than the input itself, which is sort of difficult to sort of think about and consider clearly. So I prefer this definition we're using. Okay, so now I want to just introduce a couple of complexity classes here, so-called bounded error probabilistic polynomial time. So remember, we have our decision problems. A language is a subset of bit strings, and it's decided with bounded error if you have a probabilistic single bit output from the circuit CW that does the computation for W, and if the word is in the language, you output 1 with probability at least 2/3, and if you're not in the language, you must output 0 with probability at least 2/3. So if you think of 1 and 0 as being yes and no, the computation has to give you the right answer with probability 2/3 in each case for every input. And so it's bounded error means we're bounded away from a half here, and it's well known that this number 2/3 is not significant here. You get exactly the same class for classical circuits called BPP, for quantum circuits called BQP. You get the same class for any number here that's strictly between a half and 1. In place of 2/3, there's a standard technique of improving your success probability of running the process several times and doing majority voting on the answers to repeated runs. Okay, so I won't elaborate on that here. And then there's another class called PP, which we'll be coming to later on. It's called unbounded error, and this is where the probabilities, you still have to get the right answer always with probability more than a half, but it doesn't have to be bounded away from a half anymore. It's simply greater than a half, but these probabilities could approach a half exponentially closely as the words get longer and longer. Now this is a very fragile class. It's kind of non-physical in the sense that if I had greater than or equal to a half here in both cases, that would be completely trivial. Every language has that property, because all you do is you ignore the input and just toss a coin and just say yes or no according to whether the coin comes heads or tails, and that's always going to be correct with probability a half, right? So you don't solve anything. So it's just the fact that it's greater than rather than greater than or equals to that gives you. So it's very, very fragile in sort of changing these conditions, and it's a very big class. It's easily seen to contain NP and other things like that. Okay, but it's very useful for sort of theoretical considerations. Okay, so now for the remainder of the talk, I want to in turn consider 3 interesting classes of quantum circuits and their classical simulation properties. And the first one is a rather simple thing, which hopefully is perhaps even familiar to many people. As you know, it goes back a long way, and you read about it in all textbooks. And these are the so-called Clifford circuits and the Gottesman-Knill theorem. So let me just remind you about what these things are. So recall we have the Pauli one-qubit operations I, x, y, and z, and multiples with plus or minus 5. And the Pauli group on n qubits is simply the group generated by all tensor products of n of these things. So it's a subgroup of the full unitary group on n qubits in dimension 2 to the power n. So that's the Pauli group. And then a Clifford operation is simply defined to be any n-qubit unitary operation which has the property that if you conjugate a Pauli product, you get another Pauli product back. Okay? If you put a general unitary in place of C here, then this Pauli product will just get mapped into some, any old great big unitary transformation. But we require it here to be very special. For any Pauli product, it should always return a Pauli product again, and possibly a different one. So that's Pauli. So it's kind of stabilizes, it's the normalizer in this sense of the Pauli group within the whole unitary group. So then you get the so-called Clifford group, all these operations. Obviously form group 2, which contains Pauli. Obviously Pauli products will have this property, but there are more interesting ones. And we know exactly what they all are, so one can prove that an operation is a Clifford operation if and only if it can be expressed as a circuit of Hadamard's one-qubit phase gates, which is this matrix here, one ion diagonal, and controlled NOT gates. Okay, so this gives a complete characterization of Clifford operations. And so, you have all the Paulis too, because P squared is Z, and H Z H is X, and X Z is Y, and so on. And so, so you get lots of other basic gates, but it's still quite restricted. And the Gottesman-Knill theorem, or at least this is not the original version, this is a variant in various essential respects, says the following: suppose you have any circuit description of these basic Clifford gates, so the whole circuit amounts to a big Clifford operation, and suppose the input is any product state, or I guess you could think of it as just a computational basis state for our purposes, and the output is, say, a measurement on a single line, say the first line, then you can always classically strongly simulate this efficiently in polynomial time. So note that such circuits can generate interesting entanglements, with Hadamard's and controlled knots. You can generate Bell states and so on and so on. And if you try and simulate these circuits using the tensor network contraction method, it simply doesn't work. You can always find circuits that will make any contraction ordering fail to be efficient. So, so we intrinsically use the extra algebraic properties of this restricted class of circuits to achieve, this simulation property. And I want to actually show you how to prove this, because this will be important for our second class of circuits, match gates, which I'll come to shortly. And so you should try and remember the structure of this very simple proof of just 3 or 4 lines. So, I should maybe say at the outset, this is not the original proof that Gottesman and Knill produced. The theorem originally kind of emerged from the theory of quantum error correcting codes and the stabilizer formalism, and this proof is not equivalent to theirs in various essential ways. But still, it's very, very simple. So, okay, so suppose C is any Clifford circuit, made up of those Clifford gates, and the input is some product state, A1 to AN, and suppose the output probability is P0 to P1, then if we write Z1 as, Z on the first line and identities on the remaining of the n cubic lines, then the expectation value of this thing in the final state is the circuit applied to the initial state. So the expectation value in that is the difference of the probabilities. This is just the standard quantum rule, because the eigenvalues are plus or minus 1 of z. So the difference between the probabilities is just this. So here's the final state, the adjoint, the bra vector for it, here's Z1 in the middle. So if you look what we've got here, we've got Z1, this object here, which is a Pauli product, you notice, getting conjugated by the gates of the circuit successively. And then you get the whole circuit conjugated. Since they're all Clifford operations, all of these successive conjugations preserve the Pauli product structure of the thing you develop here. So this potentially exponentially big thing you get in the middle here always just passes through these Pauli products, and at the end of the circuit you get some p twiddles, the Pauli products, wedged between these product states, and everything factorizes. The A's latch on to the corresponding P's, and this potentially exponentially big calculation here factorizes into n 2x2 matrix calculations, which are obviously computable in classical polynomial time. So you can easily compute the difference of the probabilities, and since they sum to 1, that amounts to a strong simulation of the circuit. Okay, so this gives a full proof of that theorem. Except there's one slight thing I glossed over here. You need to know what these Paulis are at the end, or as they proceed through the circuit. And so there are these update rules that tell you how specific basic Clifford gates change any Pauli product. And those update rules for these Pauli products, telling you how to eventually get these p-twiddles, are easy to compute classically as well. I mean, after all, it's not surprising because each 1 or 2 qubit Clifford gate only changes 1 or 2 of the Paulis in this product at the locations that it's acting on. So it's not at all surprising that they're all very simple computations to update classically. And then so then you get this simulation. So okay, so I want to make a couple of, you can say some more interesting things about this. So the first remark is that this update rule I've just been talking about, it's clearly computable in classical polynomial time, but if you look at it more closely, you don't even need the full power of classical polytime to do it. It turns out it suffices to just compute bit sums mod 2, which is weaker than classical polytime. So in fact, it turns out although these circuits are simulatable, they're actually not even that. They're weaker than classical polynomial time, these quantum circuits. And Aronson and Gosman were able to characterize precisely what their computational power is. And what they proved is that classes, the languages, the class of languages that can be decided by log space uniform families of Clifford circuits, and as I'll say later on what log space means a bit more, it can be identified precisely as this classical class known as parity L, which is slightly one of the less well-known of the several million classical complexity classes defined. But nevertheless, it's interesting that the power of Clifford computations can be precisely characterized in this sense. So parity L is, well, the principal definition is log space non-deterministic Turing machines that accept, if and only if an even number of paths accept, and language is decided by such things as this class. And I don't want to explain what this means, but you should just be aware of the fact that the power of this computational class here of Clifford circuits can be characterized in a precise way. So, second remark is, given that the Clifford circuits are rather weak, even compared to classical polytime, it's interesting to note that if I throw in any other 1 circuits, and the corresponding main theorem here is Valiant's theorem, which was first proposed by Leslie Valiant, the computational complexity theorist, who also has an interest in quantum computing. So let me first explain what this theorem says and what the ingredients are. So a match gate is just any 2-qubit. It's always a 2-qubit gate of this special form. You have PQRS on the 4 corners and WXYZ in the middle, and you have zeros in the remaining slots. And so if you call A and B the matrices of, PQRS on the corner and WXYZ in the middle, then I'll write this gate as GAB. And you see what this structure amounts to is the one, it's this 1-qubit gate, if you like, A, acting in the even parity subspace of double 0 and double 1 subspace of 2 qubits, and the B in the middle acts in the odd parity of 0, 1, 1, 0 subspace. So if you were to reorder the basis from the standard ordering, it would block diagonal lines into these 2 subspaces. So you require that both of these ingredients, this A and B, be not just any old unitary matrices, but they both have to be in SU2 or U2 with the same determinant. So apart from that, though, they can be arbitrary, different unitary or SU2 matrices. Okay? But they have to have the same determinant, which amounts to them being in SU2 with an overall phase out front. Okay, so it's a rather interesting kind of gate. It's got lots of parameters in it, unlike Clifford gates, which are rather discrete. There's lots of stuff you can mess around with here. And Valiant's theorem says the following. Suppose I have any circuit of match gates, the description of it, some size, and the following conditions. The match gates are allowed to act only on nearest neighbor qubit lines. They're not allowed to act distantly. So slightly unusual sort of condition. The input is any product state, so for our purposes just think of a computational basis state. And again, the output is a Z measurement on any single line, just like for the Clifford circuits we were just talking about. And so instead of Clifford circuits, we have these nearest neighbor match gates. But then again, you can classically, strongly, efficiently simulate any such thing. So these circuits are rather interesting. Valiant's original proof comes from a very unusual direction, at least for our community, from the theory of counting perfect matchings in graphs and weighted graphs and so on. And later, when physicists started looking at this result, Kneel and Tal and DiVincenzo realized that it has a close relationship to an already known theory of non-interacting fermions, so-called. So if you're a physicist, you might know what they are. And in fact, a different kind of statement of this theorem effectively already existed in the literature of sort of many-body quantum physics of fermions. But it was particularly useful to kind of phrase it in this way. Okay, so I'll again give a simple proof of how this works, but before then I just want to make a couple of remarks, like the remarks we just had about Clifford circuits. And like Clifford circuits, it's possible to characterize the power of match-gate circuits as well. They turn out to be weaker than classical polynomial time, and I'll say a little bit more about that later on. And the second remark is this issue about nearest neighbor action. And so remember, for Clifford circuits, we had this idea that if you throw in any 1-qubit gate, which you might think of as a rather simple object, you regain full computing power, quantum computing power. Here you get a much more dramatic such example. It turns out that if you allow your match gates to act not just on nearest neighbor lines like this in your circuit, but only on next nearest neighbor lines, just one more line further apart, then you regain full universal quantum computing. So this tends to worry some people. It sort of indicates nearest neighbour line, you can do that if you have a swap gate. Because you can swap the line to the nearest neighbour position and then swap it back. And so in other words, the swap gate is enough to restore full quantum power here, and you don't even need the full power of the swap. You only need to use it in isolation. You never even need to swap distant lines near each other, only just one further line apart. And then it becomes even more unnerving, as I say, when you realise that the swap gate is actually trying very hard to be a match gate but doesn't quite make it, because what does the swap do? It's the identity on these guys, and it interchanges these two. So swap is actually GIX. You know, it almost looks like a match gate, but the trouble is the determinant of x is -1 and not +1. So this is not a valid match gate. And it's only that minus sign, if you like, that saves the whole day for quantum computing being simulated by this method. So you get these sort of amusing things, and it does make you wonder, how much more powerful is quantum computing really than quantum computing. So I was going to include a proof of this, but perhaps I'll omit that and move right on to going back to Valiant's theorem now and indicating how you prove this result. And again, there's kind of a nice, understandable proof that parallels very much the Clifford proof that I gave before. You just need to find the right starting point, and then everything comes sort of fairly easily. But the starting point is completely not obvious. So what we do is, out of thin air, we write down the following 2n Pauli product operators. So I've left out all the tensor product signs. So these are not multiplied together in tensor products on n qubits. So there's 2 of them associated to each of the n qubit lines. And the first pair, C1 and C2, you have x and y, the Pauli x and y, and then you have all identities. And then for the successive lines, you move the x, y into the corresponding line position, and you put z's on the left and identities on the right. Okay, so generic ones like this, you have x and y's in the middle somewhere, all z's on the left and all identities on the right. So this set of 2n operators are the so-called Jordan-Wigner operators, which were written down by Jordan and Wigner way back in the 1930s to solve certain kinds of many-body problems. And they satisfy these algebraic relations. They anti-commute, so CIC plus CDCI is this, which means different ones anti-commute with each other, and they each square to the identity. So those algebraic relations define what's called a Clifford algebra on 2n generators, an abstract, mathematical algebraic structure, if you like. And what I want to introduce here, which I'll call Pn again, by analogy with the Pauli group, but here it's defined to be the linear span of these 2n operators. So it's a 2n dimensional vector space. And introduce Cn as the set of all nearest neighbor match gates. Then what we begin by showing is that nearest neighbor match gates normalize this linear span. Just like the Clifford operations preserve the Pauli group under conjugations, nearest neighbor match gates it maps any one of these things here into a linear combination of them. So it stays within a linear span. Okay, this is the basic idea for the classical simulation. So to prove that normalization property, you could just take a general match gate and perform the conjugation directly with a little bit of after a few pages of calculation. You see that this works. It's not particularly deep, but it's nice to see that there's this very elegant mathematical theory that kind of envelops this formalism. It's kind of a consequence of some different symbols. They're not those particular matrices I wrote down before, and they're required to satisfy these algebraic relations. And you consider the algebra generated by products of these things and sums of those products, and a general vector in that algebra is simply a formal sum of products of the C's, where without loss of generality I can assume these indices are all different and in ascending order. That's because if they're not in order, I can just anti-commute them with minus signs to put them in order, just with plus or minus signs for coefficients, and if two of them are the same, they get squared out, because C squared is the identity for any two. So the dimension of this algebra as a vector space is 2 to the power n, because the number of these things here, these products, is exactly the same as the number of subsets of 2n things, which is 2 to the, that should be 2 to the 2n dimension, number of subsets of 2n symbols. And the Jordan-Victor operators, those particular matrices I wrote down on the previous slide, are precisely a matrix representation of this algebra. They're an actual realization of this abstract structure in actual matrices, and they're Hermitian as well. And if you are a physicist, then I just point out here the connection of this structure to fermionic physics. When you study fermions, you have these creation and annihilation operators, the A's and the A daggers, and these are just the standard commutation, or rather anti-commutation relations required for fermions. And if you just define the C's to be the Hermitian and anti-Hermitian parts of these operators, then the fermionic relations are easily seen to imply these Clifford algebra relations here. So I think these are called Majorana spins or whatever in fermionic theory. Okay, but we won't be needing any of that. Okay, so back to this abstract algebra. So given these C's, I can consider quadratic expressions. So let's consider quadratic expressions in the algebra like this. And I require them to be Hermitian. So taking the C's to be Hermitian and the fact that they anti-commute, it's easy to see that without loss of generality, this coefficient of real numbers here can be taken to be a real anti-symmetric matrix of size 2n by 2n, because there are 2n of these C's. And let's introduce the so-called Gaussian gate, which is simply the exponential of such an expression in the algebra. So you just call e to the ih, where h is one of these guys. And in the abstract algebra, this is just the power series. You define the exponential as the power series, and we know how to add and multiply these C's together, so you can compute these things as abstract algebraic objects. And then we can prove a basic algebraic theorem, is that whenever you have such an object, which is an exponential of one of these quadratic things, if you conjugate any one of the basic generators, you get back a linear combination. And furthermore, the coefficients in this linear combination here always form a rotation matrix. It's not just any old 2n by 2n matrix, it's always a special orthogonal matrix. And in fact, one can prove that it's just the exponential of 4 times this coefficient matrix, and it's well known that anti-symmetric matrices exponentiate to give you rotation matrices. So this is a rather special property, and this is what's useful in our simulation process. So basically, this is the property I was essentially claiming works for match gates. So if we now go back to this Jordan-Victor representation of the Clifford algebra, and so these are particular C's, I can compute what these Gaussian operations are. I can exponentiate, these quadratic things, and it's not hard to see that nearest neighbor match gates are always examples of such Gaussian gates. So the previous algebraic theorem gives the result we want. So for example, I've just written, you can actually do this without any calculation at all. two lines. So on the first line there are two C's associated with that, and the second line is C3 and C4. And if you look at all the quadratic terms, when you multiply the Jordan-Wigner, the four things you have, two lines, you just get these expressions. And you can see that these expressions all preserve the even and odd parity subspaces, because either you have things like Z and I, which map zeros to zeros and ones to ones, perhaps with a minus sign, or you have X, Ys and Y, Ys and X, X's, and these guys, each of X and Y switches zeros and ones. So it's going to map double zeros to double ones and vice versa, and these into each other. So all of these operations respect this decomposition of these two subspaces, so hence the exponentials will as well. And you have 6 parameters worth, and the only thing you could possibly get is you have to get unitary matrices, and the full space of SU2 SU4 matrices that preserve these two subspaces is SU2 plus SU2, and hence you must get match gates out of these exponentials. So you don't actually have to do any specific calculation at all. And similarly, one can show that all nearest neighbour match gates are Gaussian gates, but Gaussian gates are more general objects because you can add in all of the 2NCs can appear here, rather than just 4 of them associated with 2 consecutive lines. And one can prove, but I won't even indicate how to prove it, that any Gaussian gate on n lines can always be expressed as a circuit of nearest neighbour match gates. So although Gaussian gates appear to be more general, and nearest neighbour match gates are special cases of them, they're not really more general if you're allowing yourself to make circuits of match gates as well. Any Gaussian gate can always be represented as a circuit of nearest neighbour match gates. So they already capture everything you want. Okay, so now to prove Galileo's theorem, it's just like the Clifford circuits that we had a while ago. So going back to the linear span of these C's, so suppose I have such a linear span, if I conjugate it by any nearest neighbour match gate, what we've just indicated is that you get another linear span, and the new coefficients are related to the original coefficients by a linear transformation, which is always a rotation matrix, and if it's a nearest neighbour match gate, it acts on only 4 of these C's, and this rotation matrix acts non-trivially only as a rotation matrix from SO4, so a 4-dimensional rotation matrix, and it's the identity for all the other C's. And also, you know, the difference of the output probabilities, just as we had before, is the expectation value of this Z1 in the final state. And in the Clifford case, Z1 was in the Pauli group, it was in the thing we're considering here, but it's not here. Z1 is actually a quadratic expression in the Jordan-Wigner operators, as you can immediately see from the definition. C1 times C, you get X, Y is I, Z. So the Z1 there is this product. And when you conjugate that, well, that's still okay because I can slip another, so there's the U dagger on the outside. I just slip another U dagger in the middle, which is the identity, and then look at these 2 linear conjugations, and what you finish up with is not a great big exponentially big mess in an exponentially big Clifford algebra, but only a quadratic sized expression. So you get about an n² sized sum instead of an n sized sum, and they're product terms. So now each expression, each one of the terms in this sum is a product operator. It's a product of Pauli's because the Jordan-Wigner operators were special kinds of products. And if you evaluate them, if you wedge them between product states, then just like in the Clifford operation case, you can classically compute that because it just factorizes down got a sum, but the sum is only over n squared terms, so everything just stays polynomially big, and if you sit down and look at all the details of this, you see that everything is computable in classical polynomial time, and that gives an explicit simulation of these nearest neighbor match gate circles. And again, it's interesting to have a closer examination of what's actually involved in this classical simulation, and you see that it proceeds by multiplying together 2n by 2n sized matrices, which are rotation matrices. It's these conjugate actions of the match gates on these linear span of the Jozsa operators. And so an interesting thing is that you can exploit the fact that they're rotation matrices rather than any old matrices in a rather curiously interesting way, because rotations are special cases of unitary matrices. They're real unitary matrices, so you can think of these matrices as quantum operations in 2n dimensions, so which means logarithmically many qubits, so log n plus 1 qubit line is 2n dimensions. So what this does is it relates the computational power of match gate circuits on n lines become related to quantum processes on log n lines, a kind of exponential compression of the space you're operating on. So and one can prove formally that the computational power of nearest neighbor match gate circuits coincides exactly with log space bounded universal unitary quantum computation. So let me just say a little bit more about what all these words mean. So I guess the time has come to say what log space means. Okay, so this is classical log space bounded computation. Is the following idea. You imagine you have your computer and its memory is divided into three separate regions. There's the input region, the workspace, and the output space. And I've drawn them as kind of one-dimensional tapes here in analogy to sort of Turing machines. And the idea is that here's my input I1 up to IN, the usual sort of scenario. That's my input word of size n. But the point is, this part of the computer is read-only. You're not allowed to do computations in this space. You're only allowed to work in a separate area, so-called workspace, which only has logarithmically many cells in it. So you have to work in very cramped conditions, but you can bring down, bits of the input and work on it, and then other bits and work on it. But you can't ever work on the whole input simultaneously, because you've got woefully inadequate amount of space to even write down the whole input. And then you have an output region. You can sort of trickle out your answer and write your answer down here, which could be quite long, but often we, for decision problems, say we only consider a single cell here. Now, you might think this is sort of unnatural, but in fact it's very natural, and we do this sort of thing all the time, and probably people are doing it right now in this room, because when you access the internet, you think of accessing the internet as a computation where the input is the whole internet, the whole World Wide Web, which is certainly much too large to download onto your computer to work with, but you can look at some various web pages and bring down bits of it and do calculations, and then bring down other bits and do some more. So the input tape is the whole internet. This is your hard disk in your computer here, and this top arrow here is your browser, if you like. And so the idea is very sort of natural, or more generally any kind of external computation on a very large external database of any sort. Log space is rather special among sublinear functions, because if you've got logarithmic space here, you've got just enough room to record positions in the input, because numbers from 1 up to n can be written down in log n qubits, log n bits, to write down number n. It's a bit string. So in the course of your computation, you can remember bits of the input you went to previously and go back to them. It's a bit like remembering web pages you've already seen. So that's a rather important feature of these computations, and it's fairly easy to see that any log space computation like this that holds must run in polynomial time. It can't go on for longer than that. So the power of such computations is contained in P and is believed to be strictly weaker, although that's not proven. But conversely, a computation that just runs in polynomial time does not necessarily remain in cramped conditions here. You know, the computer could just walk along its workspace at polynomial distance in polynomial time. So we have this idea of log space computation, which is kind of a naturally weaker thing than poly time, and then quantum log space bounded computation is simply log space uniform families of quantum circuits, arbitrary quantum circuits on logarithmically many lines, or more precisely, for each input of length n, we have a classical log space computation which produces for us on the output tape a description of a quantum circuit on logarithmically many lines, that's in this exponentially compressed space, acting on input 0. So this is the computation we're going to do. So everything here is all done in constrained log space circumstances, and such things can be proved to be exactly equivalent to the power of match-gate circuits on n lines. So it's sort of interesting that the algebraic restriction of match gates rather than arbitrary gates can be characterized in terms of a pure resource-bound log space and general universal computation within a more compressed resource-bound. So it's quite rare in complexity theory to compare different kinds of computation resources. Okay, so let's say that to that's running out of time. So the third class of things I want to consider now are, so this is my final sort of kind of simulation result I want to consider. So far I've been kind of trying to indicate that the relation between classical and quantum computing might be perhaps more fragile than a lot of people would like to think. These funny extension properties where you suddenly regain full power with the addition of something that looks utterly trivial, starting with a situation that's classically simulatable. So now I want to argue the opposite point of view. I want to kind of provide evidence that there's a big gaping chasm between classical and quantum computing power, in fact. And I want to consider circuits of commuting gates. Now, these are very, very simple things. These are gates that are all diagonal on the same basis. So we're going to consider this situation. You have inputs are all zeros, and then you have a circuit of 2 cubic gates, which are all diagonal in the x basis, or dual basis. This is 0 plus or minus 1 basis. Okay, so we have gates that are all diagonal in that. And I'm going to, for the output, I'm going to make measurements on some designated subset of k lines, say. And I'll have these output probabilities on k bit strings. Now I've drawn the first k lines here, but they can be sprinkled however you like, and the output lines is just the kind of pictorial convenience that I've put on top here. So clearly, if these gates were diagonal in the z basis, in the computational basis, it would indeed be totally trivial, because this 0 state would just come out as a 0 state with a couple of phases on it. And so we just view it in this sort of slightly off basis here, the dual basis. But equivalently, anything diagonal in the x basis can be written as h diagonal in the z basis h. If you conjugate h conjugations, interchange the x and z bases. So an equivalent description is simply to replace all the x gates here by h, z, h gates, and then all the h gates between pairs of gates in here all disappear because h squared is the identity, and the only h's that remain are all at the front and all at the end. So equivalent to this, we get the following thing, which we could consider, and sometimes easy to think about. You start with zeros, you apply a layer of h's, hammer marks, to every line. You follow it now by a circuit of z diagonal gates in computational basis then you finish off with another layer of H gates, and then you measure in the Z basis. Or alternatively, you could get rid of these H gates if you like and measure in the X basis, because the H just switches the X to the Z basis. And you could throw away these lower H gates, because if we're going to measure these lines, it doesn't matter what we do down here. Okay, it's not going to affect the measurement outcomes. And indeed, for everything I'm going to say, it will suffice to not even have complicated diagonal entries. It's enough that all the diagonal entries are powers of the 8th through the unity. So there's only 8 different things we need to consider here. Okay, so this looks like a very simple situation, and most people's immediate reactions say, okay, well, give us half an hour in a quiet room and I'll tell you how to simulate these things classically, because it's so simple, right? And then they come back a couple of hours later saying, well, I couldn't really figure out how to do it. And this is the reason, basically. So the bottom line of this section is the following. If the output of uniform families of such, I call them IQP circuits, so these commuting gates, that's instantaneous quantum polynomial time. So instantaneous because, you know, in physics, commuting operations can be applied simultaneously, but for us, they're just commuting gates. So if you could simulate these things classically, even weakly, not even strongly, and not even weakly, but weakly up to a very generous error tolerance, up to 41% multiplicative error, and I'll say in a moment what that means. If you could do this very weak classical simulation of these circuits, then it would have this catastrophic consequence for complexity theory. There's an infinite hierarchy of complexity classes called the polynomial hierarchy. It's a tower of classes, and if this simulation were possible, this infinite tower would collapse to its third level, which I mean, I don't expect, you know, I'm not saying here what the polynomial hierarchy is, but I just want you to be impressed by the fact that this is supposed to be very implausible. It's a bit like P equaling NP, although unfortunately it doesn't imply that, but it's kind of similarly implausible. It's a massive collapse of sort of computational complexity classes. So, okay, so what is this notion of multiplicative error? So, a probability distribution R approximates a distribution P up to multiplicative error C, means this relation holds. The R probabilities you know, don't equal the P's, but the P's are bounded by C and 1 over C times the R probabilities. Okay, so it's a slightly odd kind of situation, but nevertheless it's the one we need here. And we're allowed to make C as large as root 2 to make this thing work. So the upshot of this theorem is that, you know, assuming the polynomial hierarchy doesn't collapse, it appears that these extremely simple quantum circuits with only, you know, commuting gates will exceed the possibilities of efficient classical computation. They can achieve a task that no classical computation can do in polynomial time. Okay, so there are various interesting ingredients to this result. The first is well, the main point here is the size of this output register is going to be absolutely critical. Like, remember, like, you know, for decision problems, we only measure on one line, and you might think, well, measuring on many lines, well, that's not such a big deal. But here, it's going to be crucially important that you measure on suitably many lines, because another result we can prove is that if the output register only has logarithmic size, if you measure log n of the output lines, or fewer, then you can exactly classically weakly simulate that. So it's as though these circuits are trying to be classically simulatable, but not quite making it. So if this register is too small, then you can easily achieve this classical simulation. And in fact, it gets even stronger than that. Dan recently has shown that in this situation, when the diagonals have these values, then you can even strongly simulate it and actually compute all the probabilities that you want as well to proof of this result is pretty easy, actually. And here's, so let me just try and quickly run through this picture. So it's just this picture here. So here's my Z diagonal gates, here are the Hadamard marks, here's my input 0, and here's the register I'm going to measure with K lines, so you get K bit strings, and here's all the other stuff, N minus K lines, N minus K bits. So after the first bar of Hadamard, the quantum state here is just the uniform superposition of everything. Then, when I hit it with all these Z diagonal gates, that all these guys just pick up phases depending on the basis in, you know, the label of the basis state. So after this circuit here, I simply get a state of this form. It's just the same uniform superposition, but now you've got some phases put in. And furthermore, the phase fxy that goes with the basis state labeled xy is clearly computable classically as a function of x and y, because you just simply look at the gates that hit the appropriate lines and accumulate the phases as you go through this polynomial sized circuit. So that's really easy. Each individual one can be computed. And now, note that any subsequent things we do on register A are independent of anything we do on register B, so long as we don't have any gates that hook the two together. You know, so you know, I can apply any kind of crazy gates or even just trash B completely and throw it away, and it won't have any effect whatsoever on the output results from A. So that's what I'm going to do. That's exactly what I'm going to do. I'm going to throw it away. I'm going to measure. So instead of even doing the Hadamard, I'm now just going to measure the lines B. And what that gives you, if you look at this state, the phases don't come in anymore because they all square to the identity, and measuring B simply gets me a uniformly random Y string. So in order to get that, I don't have to measure it, I can choose that classically at random. So what I do now is I've got this expression here, I classically randomly choose a Y naught bit string, uniformly at random, and then I substitute it into this state, and I get this state here. And this state now is a state of K lines, which is only log n qubits, if this is logarithmically big. So this state is only in polynomially many dimensions. So from now on, anything I do on the register A, I can compute classically efficiently. I can, you know, apply gates, I can do measurements, I can do anything I like because this state is small enough to be able to compute everything by direct calculation. And that shows how you can simulate that many lines. And just very quickly, in the last 5 minutes, I just want to whiz through the ideas involved in proving this domain theorem, this one here, because there are some particularly interesting ingredients. So if you can classically simulate these commuting circuits, then polynomial Clara collapses. So an interesting thing is this idea of post-selected circuits. So now we're back to you know, just any kind of circuit. A post-selected circuit is this following thing. Instead of just having an output register, and instead of just using the probability that the output gives you some bit string is your output, you have another so-called post-selection register, which I call P, and you always measure this as well, and you only take runs of your process for which the post-selection register yields zeros. So in other words, more mathematically, instead of taking the probability of the outputs as being your distribution, you take this conditional probability, the probability the outputs give x, given that the post-selection register yields 0. So in other words, you know, physically to implement such a thing, you have to run this circuit many times, and you just simply discard all those runs that didn't give you the right post-selected thing, but then accumulate all your statistics only on those runs that did give this output. So these conditional probabilities are just these. This quotient by Bayes' rule, the probability of that and that over the probability of the conditioning thing. So we're going to use these as our probabilities, and it's kind of non-physical thing because you know, this probability of getting 0 here could be very small. It could be exponentially exponentially small. So it's kind of inefficient. You might have to run this exponentially many times before you just happen to see a good run. But nevertheless, it has great theoretical interest. And Scott Aronson showed some years ago that if you apply this idea to general universal quantum circuits here, then the bounded error quantum polynomial time class with post-selection gets boosted up to this unbounded classical class PP that I mentioned a while ago. So, which is an interesting result in its own right. And what we prove first is that similarly, if you add post-selection to this much weaker class of commuting circuits, then post-selection again bumps it all the way up to PP. So, so the proof of that's given here, but perhaps I won't go through it, except to say that the proof uses Aronson's result by showing that any general quantum circuit can be thought of as a commuting quantum circuit if you have the power of post-selection as well. Post-selection enables you to kind of make any quantum circuit look as though it's commuting. So, and it's not very difficult to see how that works, but perhaps I'll due to lack of time, I'll not go through that. And then the last ingredient to the main theorem is that now, if you can classically simulate these commuting circuits up to suitable multiplicative error, then the post-selected class of commuting things will be equal to the post-selected class of bounded error classical polynomial time computations. And that's because of just look at these formulas here. Suppose you have something that's decided by a family of commuting circuits with post-selection. So that means that these equations hold here. If you're in the language, the probability that you get 1 given the post-selection is bounded away from a half. And if you're not in the language, you get this with these equations. Now suppose this process that produces these probabilities could be classically weakly simulated. What that means is that there's a classical process that produces essentially the same probabilities. But if the probabilities of the classical process are quite close to these ones, in other words, the approximation is reasonably good, then these quotients in the classical case will again be bounded away from a half. You won't mess these values up too much. So if you could classically weakly simulate the IQP circuits with error C, then these quotients develop a multiplicative error of C squared, which is because it's a quotient, so it's not very hard to see. And then if C is small enough, in fact, if it turns out if C is less than √2, then these are still bounded away from a half. So then this thing in post-IQP will be in post-BPP. You can do it classically as well. So that would show these two things are equal, which then would mean that post-BPP equals PP as well. So, and then, so let me not even say what the polynomial hierarchy is here, but just to say that the theorem then follows because we simply resort to some known facts from classical complexity theory, which shows that post-BPP is in fact not very high as a complexity class. It's contained within the third level of the polynomial hierarchy, whereas PP is known to be hard for the polynomial hierarchy. There's Toad's theorem, which so PP certain probability distribution on many lines, whereas we haven't succeeded in trying to concoct, well, in producing any kind of natural or even unnatural computational problem of like deciding some language or other whose computation depends on being able to sample one of these distributions. So it would be nice to have an explicit example of such a thing, but nevertheless this theorem still has considerable theoretical interest, I think, in the sort of light it sheds on the power of quantum computing. Okay, so I think I've already used up my time, and thank you for your attention. C is root 2 here in this formula. So 41, 1.41.4, 100 root 2 minus 1%.
So these results seem to be suggesting that quantum computation is only slightly more powerful than classical computation. Right?
This one?
Well, the theorems you've shown us today in general.
Oh, the earlier ones, yeah.
Seems to be suggesting that if you just add a little bit, you will do classical computation or even do less and get the power of quantum computation.
Yeah, that's right, yeah.
So, so what does this say about our inability to find efficient classical algorithms like for factoring?
Well, I mean, yeah, so, I mean, it's hard to know. I mean, it sort of indicates that the power of computational resources is very relative to what you've got. You know, so that's sort of a significant thing. You can have a substrate which is rather lame, and then a very trivial addition will get universal power. I mean, I guess as far as like factoring is concerned, I mean, some people believe that there will be a classical addition element for that. I mean, I think a lot of computer scientists or other fields do. I don't know how many people in this room think that there will be a classical addition algorithm. I think I would almost bet that there will be. I mean, I guess another issue is complexity theory is a very tricky thing because computational power is very discontinuously sensitive to slight changes of resources. That's kind of what these results are indicating too. And you have this in classical theory as well, I guess. You know, when you add it, it's hard to gauge the extra power that's sort of implied when you add something apparently harmless. So, yeah, so you might think that it indicates a small gap, but on the other hand, small changes can lead to large gaps as well, so that might be one way to interpret it.
If I understood correctly, you could rephrase your simple model, which was quantum very complex, which is quantum computation. Could you reformulate this in terms of match gates and swaps?
So which, sorry? Oh, yeah, yes, okay, so since match gates and swaps are universal, you could certainly express these circuits in terms of them. No, but, okay, so there's the crucial issue is the number of lines here. So in the match gates example, I was only talking about single line outputs and not larger registers. And the situation becomes much more complicated. In fact, you probably can't strongly simulate the match gates with many line outputs. So I didn't sort of emphasize that there. But in principle, I guess you could rephrase all this in terms of match gate things, but that seems like a fairly perverse sort of thing to do because, the match gates sort of work the other way around. It's surprising that they can be simulated. It's kind of hard to understand why match gates sort of work as they do. So to view something from a match gate point of view is not necessarily a useful thing, I guess. But yeah,
shown, so what's the relationship between them? Because you've shown